Hello and welcome to the tutorial of InterArtic. My name is James Ferguson and I'm the lead developer for the InterArtic tool. So InterArtic is an interactive local web application for viral whole genome sequencing utilizing the ARTIC network pipelines. So here we have the GitHub page where we have all the code. It also has extensive documentation in the README with descriptions and how it works and how to run example data. So today I'm going to be showing you how to set up InterArtic and then how to run our example data set. So to start, first of all, you have to look at which system you're running on. I'll be running this on Ubuntu 18, so that would be Linux. It's the same instructions if you're running Windows. You just have to have Windows subsystem for Linux installed, so you can click through here and follow the instructions. If you're running on ARM board or something like a Jetson, you just have to switch out the instructions for which binary you download, and macOS has its own instructions as well, but they follow pretty much the same instructions. And today we're going to be building from our latest release, version 0.4.1. And this just adds the VBZ plugins and a few fixes to the QC metrics. Now, if you ever get stuck or you have any questions or something's not working or you want some more features added, just click through onto the issues here. See if there's anything here that matches what you're saying, or what you're asking, and then, if not, you can just add a new issue and type away and tell us what you need. We'll get back to you as soon as we can. Alright, so setting up InterArtic. So we're going to follow these instructions here. So first of all, we need a download, so we just need to open up a terminal, and I'm going to do this in my downloads folder. So I'm just going to make this a little bigger. Alright, so this is going to happen in my downloads folder. So let's just copy paste some of these commands. So this is wget. If you don't have wget already, you can quickly install it. And so this might take just a little minute, so I'm going to speed the video up so we can get to the end. Alright, the next step is to go into that directory and then run this run.sh, which will then start up InterArtic, and that's it. And that was all done just by copy pasting all of that. Okay, so now once this is done, if you ever need to close InterArtic, you can just hit Control-C and it will kill it. And you can see inside this directory we have this run.sh command. So we'll run that again. You can see it starting up on your local machine on port 5000. So to go there on Linux, you can just hover over this link here, right click and go open link, and it will open up in your default browser. And this is InterArtic. So the first thing you'll notice is we have the software versions down the bottom here. Home takes you to the home screen. We have a documentation link. When you click that, it will open a new window and you can go through and see all the information. Everything I'm telling you here is in this usage document here. And then you can also click on About. The first time you do this might take a second. What it's actually doing is looking at all the different software versions that are installed. And this is just a way to quickly troubleshoot whether or not you've got everything installed correctly, which versions you're using. But it has some basic information, links to the ARTIC pipeline, so you know what's going on under the hood. Link to the GitHub, documentation, preprint, and again, of course, the ARTIC pipeline, which none of this would be possible without. Alright, so we click back to home. Now the first thing you want to do before you add a job is select your locations of input data. Now this is where your data is located. You only have to do this once. After that it'll save where it is even if you close InterArtic. And we have some information here that you can read. But if you're on a sequencing machine like a Gridiron or a Promethean, the default folders for that are /data. And you just have to create this folder here, sample barcodes, and then you'd put your CSV files in that. But given I'm not on a sequencing machine, I'm on my laptop, and I have a custom path, I'm going to go ahead and add that here. So I've got my data located here in this example data folder. Now this example data can be downloaded following the instructions on the GitHub. Just here, step 2, downloading test data. I've already done that. So here is my path. On a terminal, you can hit Control-Shift-C to copy it. And then I'm going to paste that in here with Control-V. And then this is going to be the same thing. I think I'll just double check that. Yes, sample CSVs. So the same thing here, but then this folder name here. Alright, and when you click confirm, it'll just check that these exist. So we'll just put some dodgy stuff there, hit confirm, and it says that it's not valid, right? So I'll just fix that up. CSVs, confirm. Alright, all set. You can see it's saved. So now that we've done that, we can go ahead and start adding a job. So this is the parameters page, and on this page there are tooltips to help you understand which field does what. And we're going to go through and start setting this up. So we're going to call this job test. When you click, or in some browsers like Firefox, you might have to double click, but on Chrome, just single click and it will show you all the folders within that top folder we gave. So I'll select the sample here, and that sample has the structure. This one here, let's have a look at tree L2. Let's go L3. Alright, so it's got this folder structure here with the FAST5 and FASTQ pass and fail folders and a sequencing summary file. That's normal for coming out of a Minnow sequencing run with live base calling on. Alright, so we've selected that. This is a multi-sample, has 10 barcodes. So we select that, and then this field appears where we can select our sample barcode CSV. Now, sample barcode CSV we have in this folder, you make one for each sample that you're going to run, or each sequencing run that you're going to run. So in this case, it's just a comma-separated list where you have the sample name here, followed by a comma with no spaces, and then the barcode. So in this case, we use native barcodes, so it's NB03. Otherwise, when we use rapid barcodes, it's RB03. This is for historical reasons, but just follow that, and it will automatically name all of your samples for you. All right, so back here. So we've selected the sample barcode. Then with the output folder, this is an optional field if you want to say where the output should go. Now you can just give it any name, and it will appear under this directory here. So it'll under this directory here. If you give it nothing, the default will just be output. Now this is where we can select the virus. So this one was SARS-CoV-2. The primer set we used for this was the Eden 2500 base pair primer schema. And when you select these, it will automatically set the top directory and primer scheme information, as well as when you do it for, say, Ebola. There's also this option for custom, and in this case, you just give you the same top directory in the same structure as it is here, so all the way through to the top directory of the schema. And then the primer name of primer schema is this name of the virus and then the version information. And this is just based on folder structure. So if we look at the InterArtic bin primer scheme folder, so here are the primer schemas, and we go into that, you'll see it has ARTIC Eden Midnight. So that's what this bit here is. And then you'll see if we look at, say, Eden, it has the virus, and then it has v1, and then it has all the files, the reference file and the schema bed file. So if you are doing a custom run, so let's say you're doing Ross River virus or some other kind of virus that would be compatible with the InterArtic tools, you can give it a custom name for your primer description. So this just allows you to say what virus it is, for example, so a Ross River virus. And then you can copy paste the top directory and then in the primer scheme information. So you just want to keep the structures all the same. Now in this case, we're doing coronavirus with the EDA primers, and then we come down to demultiplexing. Now this one is not demultiplexed just yet. It did not have live demultiplexing on with the live base calling, and it also has not been demultiplexed with Guppy demultiplexer, the Guppy barcoder. So in this case, we're not going to select this, but for those who do have live base calling with demultiplexing on, if you select this, it will just skip the pour chop step, and it will do everything else as usual. So we're not going to select that for this sample. Now we use the ligation library prep for this one, but you can also choose the rapid kit if that's what you use for the rapid barcodes, and it just changes some of the underlying parameters of how that's done. And then we're going to select which pipeline to run. So in this case, we're going to select both, and that's going to allow us to run both Medaka and then right after it Nanopolish. Now if you just choose one or the other, Medaka just uses the FastQ files, where Nanopolish uses the FastQ and FastFi files. They give very similar results. We tend to favor Medaka over Nanopolish, though do note that if you are running on ARM or the new M1 CPUs in the new MacBooks, Medaka will not work. This is a limitation that is known to the ONT devs of Medaka, and it's because of the new TensorFlow not working on M1 just yet, or being very difficult to compile. So if you are running on ARM or the new M1 MacBook, just select Nanopolish. But for demonstration purposes, I'm going to choose both. And then there is the customized parameters for advanced users. Now in here, depending on the primer schema that you chose, if it's already here, it will give you the minimum and maximum length of the reads. Now because we're doing a ligation, we expect them to be about 200 under or 200 over the actual length. So the length is 2,500, so we've selected 2,300 to 2,700. If, say, we chose ARTIC v3, for example, it would go between 300 and 500. And if we chose the rapid kit for, say, the midnight primers at 1,200, you'll see here goes between 300 and 1,400. The reason we do 300 as the minimum is because you can get variable lengths with the rapid kit. So we have a much larger range, but with the rapid kit you have less likely chance of having concatenaments, which is what this is all built to remove. So with ligation, back on the eating kit again. All right, so number of CPU threads. So this is how many CPUs you're going to use when doing the Nanopolish, pour chop, or Medaka steps, and other mapping steps. So 4 is fine for running single jobs. I'm going to boost this up to 6 because I have 8 on my laptop, just to make it a little bit quicker. And then normalized depth just gives you a maximum depth on the across the amplicons. If you've got wildly different depth, or the sequencing ran for a very long time and in the thousands, this will help speed up everything and stop giving you false positives on variant calls. This debugging is explained in the documentation, but we will ignore that for now. So once you have everything sorted, we will submit job. It will check that everything you've entered is correct, and if it's all good, it will start sequencing. So this is the progress page for this job. You can view the parameters of this particular job with this. You can see that it's run the gather command, and now it is running the demultiplexing command. So it'll be running it on this FastQ file. Now at any point you can go back to home, and you can see that the Medaka and Nanopolish jobs are in the queue. So you can click on any of these to go through to the progress page. Currently this is in a sequential mode where only one job will run at a time. So once the Medaka job is finished, this Nanopolish one will start. And you can see all the parameters here. So you can go back home and then go back to test Medaka, and you can see it going. So we're just going to let this go. All of the standard output from the ARTIC pipelines, as well as the work that InterArtic does, gets put into this output box here, and it will go very long down the bottom. And we're going to skip ahead in the video to when this is complete. This should be a abort button, which you can click at any time, by the way, to abort and delete the data. But while this is running, I'll just speed up the video so we can see, and this big abort button should turn into a success button. I'll see you back when that comes. Okay, and here is the end of the test Medaka. You can see that 4 out of 4 steps are complete. This button is now changed to success, and this go to output has popped up. You can see the output here of all the different parts of the pipeline that are provided by the underlying ARTIC scripts, and then some of the magic from InterArtic at the end. And we can see it's finished running. If there's any errors here, you'll have a big red box up here that tells you some errors. Sometimes if you just got a negative control in there or something, that can happen and the results are still valid. But just read the errors carefully and check the output to see why. Now once we click go to output, this might take a second. It's just processing all the output data and preparing it for visualization. And it has to do this once. So just be patient. It can take about 10 seconds. And then the output screen appears. Now you can always go back to progress from here and go back to this screen, and you can see it happens straight away. Now you can click on this box and go to the desired output you want, or you can just hit view and it will bring up the first one. Now the first thing you can see is it gives you the sample name here, and you can see this is named with the virus, the primer scheme, which version, which sample it is, the the input folder, the name we gave it, which was test, and then because we ran both test Medaka and a Nanopolish, it also adds in this test Medaka. It's a little bit redundant because it still adds the type of pipeline at the end, but it's just to separate the names in the database, and then which barcode it was. So then the first thing that you see will be this variance in coverage plot, something we call a cover plot, where you have the amplicon pools at the bottom here, and then each one of these areas is the coverage across that amplicon. Now this is used so you can quickly view whether or not an amplicon had enough coverage on it. So you can see this one here, for example, is a bit lower than the others. The dotted lines are the combined coverage, so where they overlap. You can quickly check on overlaps here. The variant that's detected, for example, penetrates both amplicons there. And then if you scroll down a little bit more, you can see all the actual variants and their positions and their associated depths. And then we have a QC table that gives you some more information. So the number of reads, the average length, quality, and then how much the mean coverage across each of those amplicons, if there's any failed amplicons, and then your total past variance with their read support, which genes that those variants fall under, and then the genome size, number of ends that were called, the percentage that you have, and then across the different auth regions, like how much of that thing. So this one got 100% on everything, but if you can click next sample and it goes to sample 4, and you can see you can keep going across and looking at all the different samples, and if we go all the way across to sample 11, you can see this one had some amplicons that failed. Now if you scroll down, you'll see that there was 2 failed amplicons, 3 and 9. So you can see here 3 and 9. This one just scraped through. and you can see that the ORF regions weren't all covered. So ORF 1AB was only covered 82.77%. Now you can also download these QC tables for all the samples. That will give you a TSV file, so you can select that and save it. You can also download the individual FASTA file for this, or you can download all the files as a single FASTA. So we'll quickly do this and save that here. And then if we go to the Pangolin COG website, we can open this file, this one here, and copy that into there, and it will automatically test all of these different reads and give you the lineage assignment. So we'll just let that run and come back to it in a minute. Now that was for Medaka. Now you can click home and we can click on the test Nanopolish, and it is also complete now. And you can see the big success. Go to output, has to process the output data. Just wait for that to happen. And there we go. We can view all the Medaka outputs as well. If we go to sample 11, you'll see it has the same dropout of those amplicons. And if we go across to sample 12, you can see the penetrance of some of these variants is pretty low. This is still, start analysis. My bad. Now, when you're running InterArtic, you have to make sure that in this window this is still open. If you close this, then the web application will stop. So you have to just keep that running in the background. Now, if we want to actually go to the data that was done, if we look in this folder now, into the example data, this is the folder that we gave it to process. And if we look at that, it now has this output folder under the first top folder. So if we go into that one, you'll see Medaka and Nanopolish, so they're the two ones it runs. So let's go into Medaka and have a closer look. And you'll see it has the initial quality control that ARTIC does. It has the combined metadata file that you can look at. So we can see this has all the metadata for each sample. And then in each one of these folders is the sample information. This all commands log is where if you've got any errors, you can look at that log to see what happened. So let's go into, say, number 12 here. And in this, we can see if you do an ls LTR, you can see the order in which all the files are created. And so the most important ones here are the pass VCF. So these are the variants that are called. We get all the coverage and depth from these files here, and we get the consensus file from this consensus FASTA file. If you want the plots, you can find them here. They're saved for you. But you can also go to any of these and click Save As. Now sometimes if you go to save this, it won't actually work. You'll get this failed network error. This is just a bug we haven't quite figured out yet. So a quick solution to that is right click, open image in new tab, click on the tab, and then you can go save image as, and it will work just fine. There you go. Okay, so let's have a look at these, and you can see these are all the lineages that have been assigned to each one of these samples. You can also do this with the command line and you'll get the same answers. And that concludes the tutorial of InterArtic. Please give us any feedback if you have any questions. Remember, read the documentation if you're unsure of something. If you're trying to design for a different or new virus, the custom primer section here will help you understand how all of that works. But we also have a look at the ARTIC pipelines documentation as well. And with that, thank you very much.